and I'm a lot more educated now. So thank you very much for the presentation today. And I hope you are able to stick around and see what some of our teams have done. We have, I believe, 5 or 6 teams that are presenting today. We've got Madison West High School, Auburn, Notre Dame, Whitney Young, and Puerto Rico presenting today. So we're going to go in that order. So we're going to start with Madison West and Allison. Do they know how to start their presentation?
Yeah, so when you guys come up to present, you're going to go ahead and share your own screen with your presentation, and then anybody who wants to talk for your presentation can just unmute their microphones and speak. Just make sure that you don't have too many microphones open at the same time. Once you guys are done with your quick presentations, I'll open up the chat for any of the other teams to ask you guys questions. So whoever is presenting from Madison West, you can go ahead and take over.
Mike, I'll just mention we do have some industry professionals watching today, and all of you feel free to chat questions to Allison also, and she will field or distribute those questions at the appropriate time. So thank you.
All right, Madison West, whenever you guys are ready. And Ella, yes, I can see your presentation. You had it bigger before. It's a little smaller now, but we can still see it.
Okay, thank you.
Okay. Good afternoon, everybody. I'm Masley, and we are Madison West Rocketry, and this is our project Fjorgan. Our project is creating a short-range land surveyor using a combination of plant health mapping and 3D modeling. We have 2 payloads on our vehicle. The first uses combined NDVI and point cloud data to create a biomass model of 3D plant health. And our second payload is a telemetry module that uses flashing lights and sensors on the ground to track the vehicle throughout flight and descent.
Hello, my name is Lizzie, and I'll be describing our payload project. One of the data types our imaging payload aims to collect is NDVI, which stands for Normalized Difference Vegetation Index. This index quantifies plant health by taking the difference between the amount of RGB and near-infrared light reflected by plant leaves. To generate a false colorized NDVI photo, like the one seen in the middle and right of the slide, near-infrared and RGB images are combined and processed with software. The other data type we're collecting and creating is for a point cloud, which is a collection of data points in a 3D space, each with X, Y, and Z coordinates. The image shown on the left of the slide is a point cloud that we've created using images from a sample drone image set of a quarry, which is 2 scale and contains over 125,000 points. The image on the right is of a branch, which shows another application of point clouds, which is to combine them with NDVI data to create a combination model, which allows for 3D analysis of plant health. Both of our physical payload assemblies are made of custom 3D printed structures that house electronics, including microcomputers and controllers, cameras, LEDs, and sensors. These structures are contained in couplers, which have apertures that extend all the way through to the vehicle body to allow for imaging from cameras and flashing from LEDs to be detected from the ground. This year, to test the feasibility of our payload hardware and software without needing to launch a full-scale rocket, we've used a Phantom 3 standard drone our club bought to carry out testing. To do this, we designed and built a customized version of our payload module to accommodate features of the drone, like attaching the payload to the legs and reducing weight where possible.
All right, hello, my name is Ella, and I'll talk about the recovery system. For the payload to image the ground, it's important that the payload bay of the vehicle descends horizontally, so we've used a Y-yoke system to balance the tubing. We've settled on this scheme, which has 2 parachutes, the payload main, which is Y-yoke to the payload bay, and the booster main, which supports the booster section separately. We use Jolly Logic parachute release devices to have a single parachute function as both a degraded parachute after deployment at apogee and an inflated parachute after main deployment. The releases work by holding the parachute closed using a rubber band until 600 feet. Then it releases and allows the parachute to inflate. We also decided to have the booster and payload descend untethered from each other, so that the weight of the booster won't tilt the payload section and affect imaging. Shown on the left is a comparison of our original and revised parachute schemes. You can see that originally we had 2 drogues and 1 main parachute. Both the upper drogue and main parachutes originally had Y-yokes, with the idea being that the payload would descend horizontally during both drogue and main descents. This system turned out to be too complicated, filling the airspace and causing tangled parachutes. In the first picture on the left, you can see that our main parachute has deployed but has not inflated because of tangling. Using the Jolly logics allowed us to use 1 parachute as both a streamer and a main parachute, meaning that we need only 1 Y-yoke to get horizontal descent for the whole flight. The separation of the booster also freed up more airspace, allowing us to have a clean deployment overall.
Hi, my name is Amelia, and I'm going to go over some of the details of our rocket and launches. In order to save expenses this year, our team utilized Aerotech Key 1999 motors from last year's season and designed our 5.5-inch diameter rocket around it. In the model shown, the green checkered compartments represent our 2 main parachutes, and our rocket has a thrust-to-weight ratio of 17.7. Our team launched a total of 6 times this season, adjusting and learning from every experience. As stated previously, we had to improve upon our complex parachute scheme due to anomalies in Flights 4 and 5. However, we flew our adjusted scheme in Flight 6 successfully and reached an apogee of 4,179 feet, just 80 feet below our target apogee of 4,259 feet.
Hello, my name is Emma, and I'll be talking about our outreach and community. This year, we have needed to adjust in many ways to remain safe and productive in the midst of COVID-19. Our club has held 6 launches so far this year. At all launches, we require masks and social distancing. We hold all of our meetings and outreach virtually through Zoom. And lastly, during our construction process, members completed assigned tasks individually in their homes or at our workshop. We have also been able to create great outreach opportunities asynchronously and synchronously this year. Asynchronously, we gave a presentation for Super Science Saturday and led pneumatic rocket outreaches. We were able to distribute and finance 111 pneumatic rockets, along with construction tutorials and rocketry basic videos on our YouTube channel. Synchronously, we led Zoom presentations to local middle schools about the science of rocket flight, which had a total of 352 participants. We reached a total of 505 people through our outreach this year. Thank you for listening. We would now be glad to answer any questions you have.
Thank you, Madison West. So if our audience has any questions, go ahead and put those in the chat. I do have 2 right now for you guys. The first one is, what made you decide to do the imaging mapping payload? What was it that prompted you to do that?
I think one of the biggest considerations was just considering what we had done last year. We did a more biological payload, and we wanted to focus on one that was more engineering and electronics based. I don't know if anyone else has anything else.
Okay, that's great. Another question is, what are the small circles that are shown around the edges of your fins in the CAD drawings?
So this year we're using sandwich fins to decrease the weight of the vehicle. So it's 2 layers of plywood, which we've layered cross grain, between 2 layers of fiberglass. And so that gives us the strength of full fiberglass fins with much less weight. And so the circles are at 1-inch intervals, and those are bamboo rivets that go through the layers to give us extra strength holding them together.
Okay. And our last question we've got for you is, what was your greatest lesson? I'm sorry, second to last question. What was your greatest lesson learned during this project?
I think probably our greatest lesson learned had to do with the recovery scheme. The scheme that we designed initially wound up being, it was too complicated to work consistently. And so I think our biggest lesson was learning that in order for something like that to work consistently, it needed to be designed in this case, in a simpler way. And that we were sort of, I guess, maybe over-designing the scheme so that it had a lower chance of working. So that was our greatest lesson, I think.
Okay. I've got a few more questions that just came in, so I'll go ahead and go through those for the next minute or so. Let's see. What type of system did you use to render your point cloud, and what software?
So we've used a combination of open source software and some that was written and modified by us. And to keep it brief, the program is able to create photogrammetrically accurate or 2-scale point clouds by detecting the overlap of objects between 2 given photos, and then determine how large objects are based on the shift between them.
Okay. Does the Aerotech motor require an L3 certification? And why use a Jolly Logic if the altitude height at max apogee would be better for data collection?
The Aerotech motor that we're using only requires an L2 certification. So our team mentor is able to do that.
Okay.
And the Jolly Logic actually gives us horizontal deployment starting at apogee and then going through all the way through main deployment. So we get both altitudes. And really it's just about making our imaging window as long as possible so that we can collect as much data. Because whenever you're dealing with a point cloud, more images means more accuracy and more detail.
Okay. What was your budget for the project? It looks incredibly impressive and in-depth.
I don't know the specific number for the budget. Usually, I think we run about $10,000 and we get most of that money from our raking fundraiser that we conduct in the fall. Because of our school's restrictions as a result of the pandemic, we weren't able to do that fundraiser this year. So that's sort of why we used the Aerotech motor, because we had a stockpile of those from past years. So we definitely did everything we could like that to make the most efficient use of the money that we did have for this year.
Yeah, there were a lot of teams who fell into that same boat because of the pandemic restrictions. And finally, what are some applications you think your payload could have? And what do you think the use and impact of the technology can have?
One of the main applications of NDVI is being able to survey agriculture, so to see which areas of crops are healthy or unhealthy and potentially need attention. And we're also thinking that a potential application of point cloud beyond just creating 2-scale representations of terrain on Earth could also be of other planets. If we could do surveying there, we would not actually have to go there physically.
Great point. All right, Madison West, thank you very much. Up next, we have Auburn University. Auburn, are you guys ready to go?
We are.